Okay, hello, welcome. In this video I'm going to be working some examples involving non-singular matrices. I'm going to be working through linear algebra homework 3.3. Okay, so I think that before I begin, I'm just going to remind you of the definition of non-singular matrix. That a matrix is non-singular if the only solution to the matrix equation AX equals 0 is the solution X equals 0. And that's the definition of a non-singular matrix. So when they ask us which of these 6 matrices are obviously singular, well, I think that's, I wrote this homework, so I knew this was a loaded question when I asked it. Obvious to me might not be the same as obvious to you. So if you don't think any of these are obviously singular, you would just say none, and you would just investigate on the ones that you wouldn't consider obvious. And number 2, just go investigate all of them for non-singularity, right? And it shouldn't be too hard for you to row reduce them because they're all pretty quick row reducers, and you should be able to do that. So for me, I'm going to tell you that B, D, and E are all pretty obviously singular to me. Okay, I'll tell you that D and E are both they're both singular to me. I'm not sure if I said that wrong, and I'm only a minute and 40 in, but I'm not going to start re-recording again just because I may have slipped up over singular versus non-singular. Okay, D and E are both obviously singular because of that column of zeros. Okay, so I'm going to say, just a second, bring some paper in here. Which of the matrices above are obviously singular? So I would say number 1, B is obviously singular because the second column is just twice the first column. Okay. I would say that D is obviously singular as well because of this column of zeros and E. So, and maybe I think I can probably row reduce these pretty quickly just to show you why they're singular in a second. Okay, which could be, okay, determine which are non-singular. Okay, now, if I'd really been, this was the best homework I could have made it, I would have had some larger ones, 4x4 or 5x5, ones that didn't necessarily look singular but ended up coming back singular. I don't think it's going to be possible to be surprised that something's non-singular. I think something looks singular and then comes back non-singular. That doesn't sound like something that would happen. All right, so for 2, we need to find the solutions to AX equals 0. So what we're going to do is we're going to row reduce A augmented with the 0 vector. Okay, I'm going to take 3 of row 1 and subtract them from row 2. So I'll have 1, 2, 0. 4 minus 6 is negative 2. But, from here, I'm going to divide row 2 by negative 2. Actually, no. I'm going to add that up right there. So I'll have 1, 0, 0. And then I'll divide by negative 2. Okay, and now I'm in reduced echelon form. And I'll interpret my solution. I have x1 equals 0 and x2 equals 0. The only way that ax equals 0 is if, all the components of x are 0, which is really what that's saying right there. So I'm going to conclude that A is a non-singular matrix. If I had to give a reason, I would say because the only solution to ax equals 0 is x equals 0. Okay, always back to the definition. So that was 2A. I'm going to need to fold this piece of paper. Now 2B is going to be, all right, this one, I'm saying it's obviously singular, but I'll still try to solve the equation Bx equals 0. And I'll show you non-trivial solutions. How about that? All right, 1, 2, 2, 4. Whoops, forgot to augment that with 0, 0. Maybe I'll just augment it, and then at the end, or I'll row reduce it, and then at the end I'll augment it with 0, 0, because I know that's how it's going to go anyway. So, all right. Subtracting 2 of row 1 from row 2, I'll have 1, 2, 0, 0. I will augment with that, because I know that's what's going to happen. Okay, and then, oh, hey, look, I've got myself, I'm in reduced echelon form. There's nothing else I can do. So I'm going to say x1 plus 2x2 equals 0. So x1 is negative 2 of x2. So let x2 equal 1. The vector negative 2, 1 is a solution to that vector equation, and it is not x equals 0. Okay, so I conclude that B is singular. But if you just thought, you know, number 1, that was obviously singular, and you didn't need to do any more work, I didn't need you to go in and row reduce it. That was just in case you didn't believe me that, you know, proportional columns gives you say, you know, in a square matrix, gives you a singular matrix. Okay, that's why it works like that. All right, 2C. All right, 1, 2, 3, 4. That's the, notice that this is the transpose of A, right? And something that I'm going to be, I don't know if I've proved it for you in class or not at this point, but one thing I will be proving for you in this class is that if a matrix is non-singular, then its transpose is also non-singular. It's going to be one of our widely accepted theorems. But anyway, I'm going to say we're interested in solutions to Cx equals 0, so I'm going to take C, and I'm going to augment it with the 0 vector, and I'm going to row reduce. Okay, I'm subtracting 2 row 1s from row 2. 4 minus 6 is still negative 2. Maybe I had something different. I made a row reduction error there. Oh, no, it just was a coincidence. It was the arithmetic coincidence. So, and then that was a 3, 0, 0. Okay, now what I'm going to do is I'm going to bring that down to a 1. As in, like, dividing row 2 by negative 2. And then I'm going to subtract row 3 of this second row from the first row to kill off that 3. And so I will have 1, 0, 0, 1, 0, 0. And I'll say that the only solution here is where x1 equals 0 and where x2 equals 0, meaning that x equals 0. Okay. All right. On to D. All right. Look, if I subtract row 3 minus row 2, I'll have a row of all zeros. And I'll have x1 equals 0, x2 equals 0, x3 will be unconstrained. I will show you. And I'll show you that I'm going to have non-trivial solutions by virtue of just letting x3 equal 1. So I think my non-trivial solution is going to be the vector like 0, 0, 1. That is a vector that you know, d times x is going to be the 0 vector. 2D. Interested in the solutions to the equation dx equals 0. Yeah. I'm going to let x equal 0, 0, 1, right? If I take that, I'm going to have 0, 0, 0, 0, 0, 0, yeah, like all 0, right? When I end up adding all these things together, and I'm not going to add anything together that isn't 0. So that is not trivial, so I'm going to conclude that D is a 6. Okay. I forgot to mention that in the previous example, if I just got the 0 vector, I'm going to conclude that C is non-singular. Fit one more in on here. All right, for E is going to be, oh, like I said, it's going to be singular because there's a column of all zeros, and I mean, you could just say x equals I, right? That will work. And I think, well, I'm not sure what the rule is going to have to be on second and third. I don't know. We'll find out. All right, for E. 2e. I'm interested in this solution to the equation ex equals 0. So I'm going to take e, augment with the 0 vector, and row reduce. All right, so we are going to subtract this down here, and to get rid of this, then we're going to divide that by 2 and subtract away that thing. So we're really going to just be left with that. And that means, okay, interpret my solution, x2 equals 0, x3 equals 0, x1 can be whatever it wants, right? If you don't see anything, there's no rules, right? We're just trying to write down the rules that these variables have to play by. Okay, there are no rules for x1. It can be whatever it wants. So I'm going to let it be 1. Okay, so this brings me the solution x equals, among other things, 1, 0, 0. Really, anything 0, 0 will be a solution to that equation. And here's a non-trivial solution. Whatever you want to put in for the first coordinate, that's a non-trivial solution, unless you wanted to put in 0. And so, if we're exhibiting non-trivial solutions, then we are at a situation where we've got a singular matrix. All right, for part F, you can't see F anymore. Okay, 1, 0, 0. All right, hopefully I want you to get to the point where you can see, okay, I'm going to take that 1, I'm going to clear out the rest of that column, then I'm going to divide by 3, and I'm going to clear that out, and I'm going to end up with the identity matrix. We don't actually have to, we don't have to do a whole lot of row reduction, especially if we see it's triangular. But maybe you're not there yet. Maybe you need to see me doing these row reduction steps, and that's why you're watching the video in the first place. I would not want to leave you behind. So for 2f, that's where we are interested in solutions to the equation f times x equals 0. Okay, so I'm going to copy the matrix. Augment with the 0 vector, and row reduce. Okay, I'm going to take, since I've already got this column cleared out, I guess I'm going to start from down here. I'm going to take 2 row 3s and subtract from row 2, and 1 row 3 and subtract it from row 1. Okay, then I'm going to divide this by 3. And in fact, if I can find my erasing thing, looks like I can't. So I'm going to write a new matrix. I'm going to divide row 2 by 3, is what I want to do. And now I'm going to want to subtract 2 of row 2 from row 1, right, to get rid of that 2. So I'll have that, which, if I'm interpreting my solution, then I know that means x1 equals 0, x2 equals 0, x3 equals 0. That means x equals 0. Meaning that f is non-singular. What's number 3? For each matrix M above, find all solutions to mx equals 0. Good thing I didn't throw this away, right? All right, so what I might do is I might go in, relabel these as problem 3. Yeah, and I'm just going to annotate on these in a new color. I do think I am going to have to go grab a new color. So let's go get some blue. Didn't have a whole lot of success. I want my bold blue pen. I'm going to actually run that down. All right, I got it. So I'm going to go back to part A. And we are answering the question, find all solutions to mx equals 0. All right, A is non-singular. That means the only solution is x equals the 0 vector. Okay. And so this is in blue. I'm working 3A. Okay. For 3B, get that out of the way and probably bring in some new color, some new area to work on. All right. So we found that as long as x1 was negative 2x2, we had something like that. So what I'm going to do is I'm going to say x equals, okay, x1 is negative 2x2, x2 can be whatever it wants, which is equal to, if I factor out that x2, I can see that this is all scalar multiples of the vector negative 2, 1. Okay? Anything that's proportional to negative 2, 1, it will be a solution to the equation bx equals 0. Okay? We're gonna have more names for that, over time, but for now that's gonna be it. Okay. For 3C, a lot of folded paper here. What I'm going to do is I'm going to say, well, if C is non-singular, then the only solution is going to be x equals the 0 vector. That's the full solution set. Okay, so that wasn't all that exciting, but we've got quite a few singular matrices in this set. So yeah, dx equals 0, x equals 0, 0, 1, so d is singular. Okay, this one I did not row reduce all the way. So we're going to need to find all of the solutions to mx equals 0. So in this case, we're looking for, I'm supposed to be working these in blue, so that's dx equals 0. So I'm going to take d, and augment it with the 0 vector and row reduce. But that shouldn't be too hard because now I've got 1, 0, 0, 0, 1, 0, all zeros here, augmented with the 0 vector. Okay, and if I would go to interpret my solution now, I'm going to say x1 equals 0 and x2 equals 0. x3, no rules. It can be whatever it wants. So if I wanted to express all the solutions, I'd have x equals 0, 0, x3, or if I factored it out the way I did in the previous example of a singular matrix, I'm going to actually say, well, it's x3 times the vector 0, 0, 1. It's any possible of 0, 0, 1, okay? Which, we'll be expressing our solutions like that as we move forward in the class, so I'm just kind of getting you started in that direction. Okay, that was D. E, we also found was non-singular. Okay. No, we found that it was singular, pardon me. I think that's twice on this video I've done this, but okay. E is singular because there were non-trivial solutions. Now, did we, yeah, okay, we found that x1 equals x1, x2 equals 0, x3 equals 0. So for 3E, I'm going to go over here and say, well, x equals x1, 0, 0, kind of like the other one, which I'm going to factor out the x1, and it's any possible multiple of that vector. And then for F, we determined that F was non-singular, so for 3F, I'm just going to, whoops, that's calculus homework. We're going to say the only solution is x equals 0 because it's non-singular, and that's what it means to be non-singular. All right, now for number 4, I am going to just kind of flash up a list of facts on a post-it note that I'm going to be just freely using without proof for the rest of these problems. All right, there you go. Here are 3 facts that I'm going to just be using freely without proof. Hopefully I've proved these for you in class by this point, but maybe not. Maybe that's something I'm about to show you next time you show up to my class. Okay, these are important facts that I'm going to want to prove to the whole class so that we can all use these facts freely without justification in the future. Okay, and I think that all 3 of these are easy enough to prove that we can get the job done here. So, the product of non-singular matrices is non-singular. If you're multiplying two things together and either of them are singular, then the product will be singular. And if you've got non-singular, then the transpose is still non-singular. Okay. Now the sum I'm kind of interested in. I don't remember just off the top of my head if that's one of our properties. So I'm going to investigate D and E, part D and part E of this problem, just to see what do we got here. So I'm going to, what am I going to do here? All right, I got distracted. I had to order some copies, and it was really getting to crunch time. So, all right, what I'm going to do right now, if I'm going to go to use these properties and work number 4, is I'm going to kind of just determine A through F, just put them all together, singular, non-singular. Okay. So, singular was B, D, and E. Okay, and then non-singular would be the other 3. That would be A, C, and F. Okay, so then when I go down here, that's a little awkward. Not sure what I was thinking there. Goodness. All right. Let's try that now. Yeah. All right. So singular is B, D, and E. So AB is a product of a singular and non-singular matrix. So I'm going to say for A, another sheet. Hold on. I could have this ready before I press record. All right. So. On that topic, okay. For A is M equals AB is singular because B is singular. For B is M equals DF. Now, that's the same thing. Okay, that's unexpected. I think I should have asked you about F squared. Okay, because I had two by two non-singular. I should ask you about AC. All right, so maybe I'll do that off to the side. B. Okay, so DF and DE both. These are singular because D is singular. Okay, let's see. But I was going to go a different direction and say AC is well defined because they're both 2 by 2. AC is a non-singular matrix. Okay, because I feel like a lot of these are going to be coming back singular. Okay. For D, on the other hand, I'm not sure if the sum, if that's a hard and fast rule about the sum of singular and non-singular matrices. Something doesn't feel quite right to me about the sum. Like it might not just be such a strict rule. So what I'm going to do is I'm going to just write down D plus F. That's what I'm interested in. Feel pretty good about if you add two singular matrices together on a factoring level, going back to the definition of non-singular, that should still admit a non-trivial solution, but I'm not sure. Yeah, that's an interesting thought. So, I don't know. That's something that I'll think about more. So, all right, what am I doing? D plus F. Or no, yeah, D plus F. So it's going to be 2, 2, 1, 0, 4, 2, 0, 1, 1 okay, is D plus F. Okay. So what I'm going to do is I'm going to investigate to see if this thing is singular or non-singular. And what am I going to do here? I don't like the look of this matrix, personally. I think what I'm going to do, though, is I'm going to try to subtract 4 row 3s from row 2. Okay, so I'll still have that. I'll have 0, 0. Subtracting 4, I'll have -2. But then once I have this one all by itself, I'm going to divide that by -2 and use that to clear out the rest of the column. And so then I've got 0, 1, 0. And, you know, I can use this 1 to clear off that 2, and then I can divide by 2 there. And so I'm going to end up with 1, 0, 0. Okay, that's not really in fully reduced echelon form, but if I know that all I'm really trying to do is find the solutions to this thing equals 0, I could augment with the 0 vector, and I could say that that means that x1 has to equal 0, x3 has to be equal to 0, and x2 has to be equal to 0, meaning to me that this D plus F matrix is non-singular. And that was kind of interesting, okay, because D was singular. So now let's think about, I don't know, I'm not sure what's going to happen with this next one. So that'll be exciting. I can see something that could potentially happen with the, you know, with the non-trivial solutions to AX equals 0, but I'm not just immediately seeing it. So I'm thinking D plus E right there. Okay, so D plus E is going to be, so 1, 1, 0, 0, 1, 2, 0, 2, 3. Yeah, that's going to be non-singular. Okay, so I don't think there's any like real rule about the sum of matrices that are singular, non-singular, whatever. Okay, so we're going to row reduce this to try to find the solutions to mx equals 0. And so I'm going to use this and subtract 2 down here, and so I'm going to have 2 minus 2 and 3 minus 4. All right, now I can I'll probably just scoot that up a little bit, and I'm going to make that a 1 and clear out that column. So I'll have 1, 1, 0, 0, 1, 0, 0, 0, 1, and I'll use this 1 to clear out that top middle entry, and I will have, okay, right, we're interested in the solutions to the equation mx equals 0, so I'll augment with 0, because I know that if I'd augmented at the beginning and row reduced, it would have still been 0s there all along. And what am I going to have here? I'm going to have, oh yeah, just all 0s, and that's the 0 vector, so that means that m is non-singular. So D plus E is also non-singular. That was interesting. M equals E transpose and M equals F transpose. I'm just going to talk about those real quick because we had said that E is singular and F is non-singular. So I'll say that for part F, you know, asking about matrix E transpose will be singular because E is singular. Okay, so that's what I'm going to say. Because E is singular, comma, E transpose is singular, period. Okay. And then same thing for part G, 4G, M is F transpose. Because F is non-singular, F transpose is also non-singular. That's going to be all for that one. Determine if the matrices are non-singular or singular. We can probably do that. Let's get some paper and let's work A, 5A. Okay, we need to find the solutions to AX equals 0. Right? So my plan is, I don't like the look of this at all, but it's going to be okay. What am I going to do here? I am going to identify, like this is going to be my main tool that I'm going to use. And in fact, I'm just going to preemptively divide that by 2, move it up to the top row, And then I'll just kind of slide everything else in, so this first row will go right underneath it. But I'm going to subtract 5 copies of this from that, which is okay. So 5 minus 5 is 0, 6, 1. 6 minus 5 of this is 1. And 8 minus 20 is negative 12. That's still going to be 0. And okay, what's going to happen to this 6, 6, 2, 8? All right, I'm going to subtract 6 of this row here. Oh, well, I can't see anything anymore. Yeah, I'm subtracting 6 of this row from that. So 0, 0. 2 minus 6 is negative 4. 8 minus 6 times 4 is 24. I almost got a little fooled by that. 8 minus 24, negative 16. And then down here, any luck, I just subtract 2 of these, so I'll have 2 minus 2 is 0, 3 minus 2 is 1, 6 minus 2 is 4, and 7 minus 8 is negative 1. Okay. Now I'm going to need to subtract this one here, this row minus row 2, and so I'll have so 4 minus 1 is 3, and negative 1 minus negative 12 is 11. Negative 4, negative 16. All right, this video it's getting to be a little long, and so I'm going to just tell you that, okay, here's what's going to happen. You're going to scale this down to a 1 and a 4. Then you're going to subtract 3 of this one from this bottom row. Then you'll have a lower a triangular matrix, which we know is going to be non-singular because we can then go and clear out the columns. So I'm just going to say that I can tell at this point, because these two aren't like proportional, that this one's going to be non-singular. Okay. So this only admits x equals 0, because I can tell how the row reduction is going to go. Therefore, it's non-singular. And then for B is much quicker on the row reduction steps. So we're going to determine if this is singular or non-singular. So we're going to be interested in the solutions to the equation bx equals 0. So we're going to take B, augment it with the 0 vector, and row reduce. Let's get that over even farther. Yeah, actually, you don't even need to see that, because that's the system we're solving. So I'm going to add 2 down both times to kill off these 2 numbers. All right, so add 2, okay. Then add 6 to negative 4, add, wait, hold on, did I copy that right? No, I did not. Okay, I worked this problem twice today in class, and that's a positive 2. So I'm going to subtract 2 of these down here. So I'm going to say it's 3 minus 2 times 3, it's 3 minus 6 is negative 3. All right, and then that's not what was supposed to happen. Hold on, what did I do here? Oh yeah, it was error I'd already made. Okay, so over here, when I had negative 1 and I subtracted 2 to get rid of that, that's going to give me a negative 3. Those are 0, 0, 0, 2, 1. Okay, now the fact that I've got two rows that are proportional to each other, I know that I'm going to bring this down to a 0, 1, 1, 0, then I'm going to add 3 down, and I'm going to have a row of all zeros, which is going to induce non-trivial solutions, and so I'm going to say that B is singular, because I've been going for a while, and that's kind of a lot. Okay. I think that I will definitely come back and prove 6, 7, and 8, but that's going to be in another video because this video is already over half an hour. Those are proofs, and those are a while. They're going to be very interesting. The proofs are not what you need to have success, say, on the quiz next time. Okay, if you can do those problems that I just worked right here, you're going to be just fine. And go back, make sure you know how to take a set of vectors and determine if it's linearly independent or linearly dependent, and then you'll be ready for next week. Thanks for watching.